Okay, hi folks. Today is day 3, unit 4, and I gave you this chart. We were going to fill it in for different types of functions. Unfortunately, I keep kind of goofing up and I've started the video a couple of times, so I'm just going to put it under the camera, kind of talk you through it, and you can stop it and take your notes as needed. You already know much of this stuff. You know the idea of domain and range, and you know that when they give you an equation, we typically just put it right into the graphing calculator and get a visual look at it. So all this chart does is kind of put all the different kinds of functions in one place just so you can kind of compare and contrast. A linear function is just a line. So it could have been 2x minus 7, 1/2 x plus 13. It doesn't matter. It's just a line. So basically it's going to look like that, right? A y-intercept of 5, slope of 3. This is just a sketch, an easy sketch. And so our domain is all real numbers. Our range is also all real numbers. Here I've shown you the 3 different ways you can write it. You can write it like that, you can write it like this, or you can write negative infinity to infinity, whatever way you're most comfortable with. And here on the end where I wrote comments, you could just make a note to yourself that all linear functions are one-to-one and also onto. One-to-one because they pass the horizontal line test only touching once, onto because they go up and down forever and utilize all the y's. Our second example, a constant function is like y equals 3, y equals 17, y equals -2. Just y equals a number, which makes this horizontal line going straight across. It is a function. Again, our domain, furthest left, furthest right, is all real numbers because it goes forever and ever out. But our range is just, in this example, 3. It's just that one y value. There are no y values down here, up here. So any of these ways, you could write y equals 3, or you can write it like this or like this. And of course, this is not a one-to-one function because it would fail the horizontal line test. It's not onto because there are y's both above and below the line that are not utilized. And then the last one for the first 3, the quadratic function is just a parabola. This is our new way of writing it in vertex form. It could be written in standard form, but you know it's a parabola, again, because it's got an x squared and a single y. In this example, it was over to the two units to the right and up 3, so I just made kind of a quick sketch. The domain, again, all real numbers. Our range, though, is 3 to infinity. It is not one-to-one because it fails the sideways line touching only once test. It's not onto because there are all these y values down here that the graph will never touch. All 3 of those first 3 are also sometimes known as polynomial functions, so I just wrote that along the side. That's just a generic term for all 3. Okay, and then we have 3 more at the bottom, one of which you're going to need to add on that step function. So we've got the absolute value function. Here I made a super tricky one, right, with a negative, which makes it go upside down like a frown. It will be 1 unit to the right and then 2 units up, and the absolute value always makes a V. So I've made a tricky version of it, but that left-right shift, the up-down shift, and whether it's a smile or a frown, follows the same kind of rules as it did with parabola. However, you could, again, just type this into your graphing calculator and get a look at it and get the visual, get the t-chart, and graph the points. Again, domain and range is all real numbers because it goes forever and ever, but the y's would be negative infinity to 2, or basically y is less than or equal to 2. It's not one-to-one because it fails this test. It's not onto because there will be y's up above that the graph never touches. And then our last example here, the functions with radicals. A radical function is something that looks kind of like half of a parabola that got tipped over. In this example, again, I just made it a little bit tricky. I put a +3 and a -1 on the outside. The -1 will make the whole graph shift down 1 unit. The +3 here makes the whole graph shift to the left 3 units. So I sort of knew what this was going to look like based on my left, right, up, down. If not, you would type it in. And again, our domain runs from -3 to infinity. Our range runs from -1 to infinity. This function is one-to-one because it passes the horizontal line test. It's kind of hard to tell on your calculator. It almost looks like it's flattening out, but it does keep moving up. But it's not onto because there are these y's down below. Now real fast, before we do our last one, take a look at all the domains. Does this surprise you that they're all real numbers except the radical? Remember on day 2 we talked about the restricted domain situations, fractions, radicals and fractions with radicals. There's only one special situation of those three types in this bunch, the radicals. And radicals had a special restriction on the domain. But we said if it's not one of those three situations, the domain is all real numbers. All right, the last example here that you kind of have to tack on the bottom is called a step function. And this is an example of one. This right here is called the greatest integer function. Greatest integer function. And I'll show you it on the calculator when you come to class tomorrow. It's basically saying, tell me the greatest integer less than or equal to x. So less than or equal to 4.7 would be 4. 4.99 would be 4. 4.99999 would be 4, but as soon as you say 5 or 5.02, it goes to 5. So our graph obviously looks like steps, where one dot is filled in and then it moves over to here and that's open, and the one right above it is filled in and then open, filled in and then open, and it makes this thing like steps. Since all the x's are used, even all the way to here and that included, the domain is all real numbers. But our range is just integers, because it just is going to happen on the whole numbers. There's these little gaps in between the y's that are not touching. It fails the onto test again because there are y values that are not used. It fails the one-to-one test because if you draw a line sideways, it would hit an infinite number of spots there. So again, those are just your types of functions, all kind of in one place on one sheet. But knowing that for domain and range of any equation, anytime, it's wise to make a visual picture of it, either with your graphing calculator or just a little sketch on your own before you start deciding function, one-to-one, domain and range type questions. All right, so that was idea number 1. Idea number 2 today is composition of functions. So I'm going to throw that under and just give you a couple quick examples, and then we'll be done for today. Composition of functions. You did composition last year with transformations. So you did it like a reflecting the x-axis composed with reflecting the y-axis or something like that. And you may or may not remember that that little symbol was like a little dot. It looks like a degree symbol, but it's typically placed in between the two things. So if we've got a function f of x and a function g of x, they could ask you for f composed with g of x. Or it might be written f of g of x. Or I've even seen it written f of g of x. And all these things mean the same thing. They essentially mean find g of x followed by function f. So you evaluate this g of x, and whatever you get gets substituted into f, just like that was true with the transformations as well. So you're always going to start on the right. You may want to make a little asterisk and remind yourself, start on the right. So you start over on the right every time and work backwards. Take whatever you got for this answer and substitute it in this direction. So let me give you a couple examples and show you what I mean. I think we will have to look at this again tomorrow in class because there's a little bit more to it, and it's a little tough to do a good job. I can't talk and write at the same time here on the thing, on the video. So f of x is x minus 3, and g of x is 5x. So suppose they ask you for f composed with g of x. Oh my goodness. Sorry. Let's make this like a 2. All right, what we're going to do tomorrow in class, the thing I just started to tell you is a little bit tough to do here in class. Is f of g of x. So, but for today, let's just use some numbers. So we're going to evaluate g of 2. So we're going to go g of 2 because we said we're always going to start on the right and just figure this out. And you'll remember from day 2 or 1, whenever we talked about function notation, that just means go to function g and substitute a 2 in right there. So g of 2 is 5 times 2. The answer here is 10. And now they want you to find f of 10. Because this whole thing was worth 10, I evaluate the g function and put the answer into f. So f of 10, we're just going to go up to function f and put a 10 in where the x was. My final answer here is 7. So f composed with g of 2 equals 7. This is like your final answer. As long as we have these two functions already defined for us, let's at the same time do the flip. Let's do g composed with f of 2. So I've changed the order. That means, again, since we always start on the right, we're going to evaluate this first. We're going to find f of 2. So f of 2 means go up to function f and just substitute a 2 right there. I get 2 minus 3, which is negative 1. And now we're going to find g of negative 1. So whatever you get for this answer substitutes back into the first expression, the first letter. So g of negative 1 would be go up to function g and put negative 1 right in there. 5 times negative 1, my answer here is negative 5. So the reason I wanted to show you these two is the question would be, is f composed with g of 2 the same as g composed with f of 2? Do they give you the same answer? No, they do not, right? So it does make a difference where you start. You have to start on the right and do it first because it makes a difference. You will get two different answers depending on what one you choose to start with. All right, one or two more examples and then we're done for today. Let's see what else we got. I'm just going to make up h of x is x squared, and g of x is x plus 2. Let's use now that different notation. It does mean the same thing, but sometimes it looks more like that, with double sets of parentheses. So they want you to find h of g of 8. We still start on the right because we always start on the right and evaluate g of 8. 8 plus 2, the answer here is 10. And now I'm going to find h of 10. So go up to function h and put 10 in right there. 10 squared, my answer here is 100. Let me show you the one other thing that I said maybe we'll look at tomorrow, but let me just show it to you now and I'll give you the idea and then we can revisit that tomorrow. Suppose they had asked you to find h of g of x. So not a number now, but just an x. What that means is they want you to take function g of x, which is x plus 2, and they want you to sub that entire function back into h, just like we just did. So I'm going to find h of x plus 2. So I'm going to put this entire thing that was g into this spot right there for h. So it's really going to be x plus 2 quantity squared, which is x plus 2 times x plus 2, which will be x squared plus 4x plus 4. So that is a rule that will let you find that every time. So now let's use this rule and find again h of g of 8 like we just did a minute ago. I would put 8 squared plus 4 times 8 plus 4. It looks like 64 plus 32 plus 4. Guess what the answer is? 100. So up at the top here I found it in two ways. I found g of 8 and then plugged into h. Here what they've asked you to do is just make a generic formula that will work for any h of g of x. And once I found the formula, I can put 8 in and just get it in one step instead of two. So when they ask you for h of g of x, you're putting that entire formula back into the first one there. All right, I've got one more for you, and that'll be it for today. They typically use h and g and f, but it could be something else. So let's just call m of x is the cube root of x plus 1, and g of x is x plus 3, let's say. And I want you to find m composed with g of 4. If you want to take a minute and try it, you can shut the video right now, hit pause, and give it a shot. Okay, I'm assuming everyone's paused and working it out, but if you're ready, we're going to start again with g of 4, which will be 4 plus 3, my answer here is 7. And then I'm going to find m of 7. So I go to function m and put 7 in for x. Cube root of 8, again, you may remember from last unit, cube root of 8, the answer here is 2. So my final answer for m composed with g of 4 is 2. All right, that's it for today. Types of functions and composition. Hope you did okay with it, and I'll see you tomorrow. Have a good night, everybody. See ya.